All right, good morning. Today we're going to get started talking about the information that is in Chapter 7 of your textbook. And in Chapter 7, we start dealing with different types of bonding. And so in section 1, we start talking about ionic bonding. And what you got to remember is that when you're talking about bonding, we're talking about taking two different elements and chemically binding those together. And the way that they are chemically bonded together actually depends on what the materials are. So when we deal with ionic bonding, we're talking about taking a metal and a non-metal. Remember, your metals are found on the left side of your periodic table, and your nonmetals are found on the right side of the periodic table. They are the things that are located to the right of your stair step line. Okay, so when we have an ionic compound, it's formed by having that metal and that non-metal come together. And when it does that, it makes what is known as ions. And these ions will have opposite charges. Your positively charged ions will be called cations, meaning they have a positive charge. And the reason they have a positive charge is because now there are more protons in the cation than there are electrons. And your negatively charged ions we call anions. And again, they have a negative charge because they've gained electrons. And since they gained electrons, now they have more electrons than they have protons. Now, the biggest thing that you need to remember is that when you're dealing with ionic compounds, your positively charged ions or your cations, those are generally going to be your metals. Your metals will form cations, meaning they give their electrons away. And your anions will be your nonmetals. They will accept electrons. Now, why are they giving electrons away or accepting electrons? The answer is they're trying to get to 8 valence electrons. We actually find that atoms are much more stable when they have 8 valence electrons. And so that's the reason they form ions at all, is so that they can get to those 8 valence electrons. Now, one of the first things that's talked about in your book is several of the properties of ionic compounds. Please remember, when you're dealing with ionic compounds, those compounds are generally going to be solid and they're going to have a very rigid three-dimensional structure known as a crystal lattice. And we'll talk some more about those in a little bit. Those crystal lattices, again, are very rigid and they are brittle. They also have very high melting points and high boiling points because the bonds that hold together these ions are very, very strong. We also find that ionic compounds, when they are solid, are very poor conductors of electricity. However, when we melt those or we dissolve them in water, then they become very good conductors of heat and electricity. Okay, so those are some of the major properties of ionic compounds that you need to be familiar with. One of the things we need to talk about is how do you write a correct formula for a ionic compound? And so we're going to start with two elements. We're going to start with two elements, and then we're going to write the correct ionic compound for the combination of those two elements. So if we start with, let's say, the element sodium, and as a second element, let's use the element phosphorus. So the very first thing you want to do when you're writing an ionic compound is you want to be able to write the symbol for each one of your elements. So we know from the periodic table that the symbol that represents sodium is a capital N and a lowercase a. And we know the symbol that represents phosphorus is a capital P. Now, if you'll remember from chapter 2, we talked about the fact that depending on what group on the periodic table we're in, that will determine what our ionic charge is. And so, in order to write a correct ionic compound, you have to know what the charges of your elements are. And so if we're looking at sodium, sodium's in column 1A, which means it has one valence electron. Remember, they're trying to get to 8 valence electrons. So sodium does that by losing one electron. All right. When I look at my phosphorus, though, phosphorus is in column 15 on the periodic table, or column 5A, which means it has 5 valence electrons. It's trying to get to 8, and the way that it's going to do that is by gaining 3 electrons. Now, the biggest thing that you have to remember with an ionic compound is that in order for your formula to be written correctly, you have to balance out the charges. And so generally the way I teach students is to look at the numbers for your ion. Don't worry about the signs for right now. We're looking at the numbers. We notice we've got a 1 for the sodium and a 3 for the phosphorus. And with those numbers, you want to find the LCM. And now you'll remember, LCM stands for least common multiple. And so if we list our multiples, for 1, our multiples would be 1, 2, 3, 4, 5, 6, and so forth. When we list our multiples for the number 3, they would be 3, 6, 9, 12, 15, 18, and so forth. All right. And now we want the least common multiple, which means I need the smallest number that these two have in common as multiples. And when I look at that, that smallest number is 3. All right. So of 1 and 3, our least common multiple is 3. And so it's my job now to get that to be a 3 and that to be a 3. And so how do we do this? The answer is we use subscripts, which subscripts will tell us how many of each one of these atoms we need. Because what you've got to remember with ionic compounds is the number of electrons that was lost by your metal had to be gained by your non-metal. And so the question becomes, what do I multiply by 1 to give me 3? And that answer is 3. And then what do I multiply by 3 to give me 3? That answer is 1. So when I write the correct formula for this compound would have 3 sodiums, so Na subscript 3, and 1 phosphorus. And now remember, 1s are understood, so we do not have to show 1s at all. And so the correct formula for that is made by the combination of the sodium atom and the phosphorus atom is Na subscript 3P. Now, no matter what your elements are, no matter what their oxidation numbers are, you have to balance the oxidation numbers to have a correctly written formula. Please also notice that in our correctly written formula, there are no oxidation numbers being shown. Oxidation numbers have to cancel one another out for your formula to be correct. So that's one of the things that we have to talk about in this section. Another one of the things we need to talk about is when we consider our cations. Let's say we deal with sodium. We said that sodium had a 1+ charge. We said that sodium had a 1+ charge. All right. Well, the first thing we need to be able to do in order to determine that charge is we need to be able to write the electron configuration for just a normal sodium atom first. And so if you'll remember, we did that in chapter 6. And so with sodium, and I'm going to write the full configuration, remember we've got to start with the first element on the periodic table, which is hydrogen, and we've got to end at sodium. And so when I do that, I'm writing that configuration as this. And then I need 3s1. Now again, sodium's in column 1A on the periodic table. That means it has 1 valence electron. So because this is a cation, that means I had to lose an electron. So the question is, when I lose electrons, where do I have to lose them from? And the correct response is you have to lose them from the valence. So how do you determine what the valence is? Please remember that your valence shell on your atom is going to be the highest energy level. The highest energy level. Now, how do you know where your highest energy level is? Well, if you have a full configuration, you just look at the big numbers that you have. And remember, only your S and P are included in your valence. And so the highest big number that we have is a 3. Now, on the third energy level, please notice that there's only one electron there. So when I lose electrons, I have to lose them from the valence first. I have to lose them from the valence first. Now, once I lose that one electron, now I see that my highest energy level becomes energy level 2. And if you look at what we have on energy level 2 in our S and our P, you'll notice that we end up with 8 valence electrons, which is what we were trying to do. Because remember, all of your elements are trying to get to 8 valence electrons. Now, again, that works very easily for an element that's in column 1 on the periodic table. But let's say we choose a transition metal. Instead of working with something in column 1, let's say we choose a transition metal. So I'm going to choose the transition metal cobalt. And if we want to write the configuration for a cobalt with a 2+ charge, the very first thing again we want to do is we want to write the configuration for the cobalt element. And so when I do that, I notice where cobalt is. I know what row and what block I need to end in when I do my configuration. So I start my configuration, remembering to list everything in order. I see that on cobalt it's on row 4, but it ends up in the D block. And I know I've got to go down 1 for my D block. So when I count over to cobalt, 4, 5, 6, 7. Now, if this is our configuration for cobalt, but our cobalt has a 2+ charge, the question becomes, where am I going to lose the electrons from? Where am I going to lose those electrons from? And again, we lose them from the valence shell. We lose them from the valence shell. So when I look at my big numbers, the valence shell on cobalt is my 4s. And I notice that I do have 2 electrons in my 4s. And so those are the 2 that I'm going to lose. And so cobalt with a 2+ charge would have a configuration of this. Now, this is actually called a pseudo noble gas configuration, and it's pseudo because it's not exactly a noble gas configuration, and the reason it's not is because with noble gases, you won't have anything in your D block after your noble gas. But if we look now, we see that our highest energy level is 3. If we consider how many electrons we have in our S and our P, we do have 8 valence electrons in our S and our P. And again, because those D electrons are present, that makes this not be a noble gas configuration, but it is called a pseudo noble gas configuration. All right, because we do have our 8 valence electrons, even though we have electrons beyond the number of electrons that are in the valence. Now, let's suppose that instead of us finding cobalt 2+, what would we do if we had to write the configuration for cobalt 3+? Well, with cobalt 3+, the only difference in it and cobalt 2+ is I've got to lose 1 more electron. So the question is, where do I lose that electron from? So I've already lost the 2 that were in the 4s. If I've got to lose an additional electron, I have to take it from the next highest energy level, which in this case would be here. So I would take one from there, which would leave me with still a pseudo-noble gas configuration because I do have electrons in that D block beyond my noble gas configuration. But again, you would see that again, those 3 electrons that I'm losing first come from the valence, but then come from my next highest energy level. So please make sure you review how to write the electronic structures for your cations. Remember when you're doing your anions, because we're not losing, we're actually gaining, you have to add those to the valence, with the ultimate goal being for them to end up with 8 valence electrons. And again, remember, you include your S and your P when you're determining how many electrons there are in your valence. Now, ionic compounds are different from covalent compounds in that with ionic compounds, you are transferring electrons. So one element loses electrons, the other element gains electrons. All right, and again, remember, we see this when we have a metal being added to a nonmetal. Well, in section 2 of chapter 7, we actually start talking about what happens when we have covalent bonding. Because in covalent bonding, there is no transfer of electrons. In covalent bonding, the electrons are shared between the 2 atoms. Okay? And now, again, when do we see covalent bonds occurring? We generally see covalent bonds occurring when we have 2 nonmetals that are in a compound together, or if we have more than 2 nonmetals, those are generally bonded by covalent bonds. Now, when we focus on covalent bonds, there are several important things that you need to understand. There are different kinds of covalent bonds that can exist. There are different kinds of covalent bonds that can exist. When we are talking about covalent bonds, I could have a compound like H2, where in that compound I have a single bond. In that compound, I have a single bond, and that single bond is represented by that one line. Now, we also could consider compounds like O2, which in O2, I don't just have a single bond, I have what we call a double bond. And so in my single bond, I'm sharing 2 electrons between those 2 hydrogen atoms. In my double bond, I'm actually sharing 4 electrons between those 2 atoms. Or I could also have a triple bond. And in my triple bond, I'm actually sharing 6 electrons between those 2 nitrogen atoms. Now, remember, when we say we're sharing, we're talking about how many pairs of electrons. So in a single bond, I'm sharing 1 pair of electrons. In a double bond, I'm sharing 2 pairs of electrons. And in a triple bond, I'm sharing 3 pairs of electrons. And again, remember what the total number of electrons that is. Now, for all 3 of these examples here, you'll notice that there is a different type of bond of sharing between those. And so when we actually start looking at these bonds, there's a couple of things that you need to understand. When we compare these 3 bonds, if I compare them, what I'm going to find out is that my single bonds are going to be a lot weaker than my triple bonds. My single bonds are going to be a lot weaker than my triple bonds. Triple bonds are the strongest because those atoms have to be very close together in order to share 3 pairs of electrons. But when I start looking at the length of the bonds, what I find out is that when I have a single bond, that bond is going to be a very long bond. But when I start talking about a triple bond, where I'm sharing 3 pairs of electrons between these 2 atoms, that bond is going to be shorter, with double bond being in the middle of both on the strength and the length. Okay? And so when we start looking at our covalent bonds, the properties we see of compounds that have covalent bonds is going to depend on the type of bonds that they actually have. Now, all 3 of these examples you see here are examples of pure covalent bonds. What does it mean to be a pure covalent bond? And that actually means that those electrons that are being shared between those atoms, they're actually being shared evenly. And they're being shared evenly because those 2 atoms are the same, so they have the same pull on the electrons. However, we can have a sharing situation where our electrons are not being shared evenly. And those kinds of bonds are known as polar covalent bonds. And because those electrons are not being shared evenly, the electrons that are being shared actually lie closer to one element than the other. For example, in the example of having a hydrogen chloride, please notice that chlorine is going to be more electronegative than hydrogen. And so what that means is that because it's more electronegative, it pulls the electron closer to it than it is to hydrogen. Now, because the electron is pulled closer to the chlorine, it makes the chlorine look like it has a partial negative charge. And because the electron is further away from the hydrogen, it induces a partial positive charge. Now, when we consider the word polar just really means charged. Okay, and so now because I have an uneven sharing of electrons, I have created what we call again a polar covalent bond. A polar covalent bond. When you have elements, though, that are the same as we had in the last example, then you'll have non-polar bonds because there'll be no partial charge. They will be sharing the electrons evenly, so there's no way for it to be partially charged at all. And again, how do you know which one's going to be partially negative and partially positive? Well, the answer is the element that has the highest electronegativity. And if you'll remember, when we talked about periodic trends, electronegativity measures how much the atom loves the electrons. How close does the atom pull the electrons to itself? And so we find that with electronegativity, the most electronegative element on the periodic table is going to be our fluorine. And so the smaller an atom is, the more electronegative it is going to be. Now, your book has a very good chart of electronegativities. You can find that chart on your homework using your additional resources that are down at the bottoms of your problems. So the element that has the highest electronegativity, that's the one that's going to get that partial negative charge. So if I look at the electronegativities of hydrogen and chlorine, for chlorine, we see that electronegativity is 3.0. When I look at the electronegativity for hydrogen, I notice that electronegativity is 2.1. So the one that gets the partial negative is the one that has the higher electronegativity value. Now, your book does get into the difference between electronegativity and electron affinity. Please just remember that electronegativity is a calculated value, where electron affinity is something that we can actually measure. And so for our purposes, it makes it easier for us to just consider the electronegativity. And so we actually can use the electronegativity difference to tell what kind of bonds we have. So when we have a compound that's made up of two elements, to find the electronegativity difference, all we do is just subtract the electronegativities. Now, if your value is less than 0.4, then what we say is that your bond type is going to be nonpolar. If that electronegativity difference is less than 0.4, then we say that that's nonpolar or pure covalent. If that electronegativity difference is between 0.4 and 1.8, then we say that we've got a polar covalent bond. And if that electronegativity value is bigger than 1.8, we say that that is an ionic bond. So elements that are really far apart on the periodic table, they generally are going to form ionic bonds. There's a large difference in their electronegativity values. And so that's why the electrons come all the way away and are being transferred to the elements. When atoms are close together, their electronegativity values are very close to one another. And that's why we can get in that polar covalent range or that non-polar range, depending on what particular elements we're looking at. Now, your book does have several examples of calculating electronegativity difference and drawing out structures as we have here, placing your partial negatives and partial positives. So please make sure you consult it. The next thing that we're going to consider in chapter 7 is how to draw your Lewis symbols and Lewis structures. We talked actually about your Lewis symbols when we did the electron dot structures. Your electron dot structures, you'll remember, that's one of your ways of showing electron configuration, where you have your elements surrounded by dots, and those dots represent the number of valence electrons. When you do your Lewis structures, though, we're talking about in compounds. How do you show those? And so what you're going to find out is that for your Lewis structures, when you see dots in a Lewis structure, those dots indicate your lone pairs of electrons. When you see lines, as we talked about before, those lines represent your bonding electrons, the ones that are being shared between atoms. Okay? And so, again, your job when you have a Lewis structure is to give everything what it needs to completely fill its valence. And again, that means we're talking about 8 valence electrons for most elements. We're talking about 8 valence electrons for most elements. Now, we're going to do an example of drawing a Lewis structure, and your book has a very detailed list of how you draw Lewis structures. I'm going to not necessarily go exactly by that list, but I'm going to help you to be able to draw Lewis structures, because that's part of what you'll have to do on your homework on WebAssign. All right, so let's say we are drawing the Lewis structure for, let's use the compound NH3. All right, when we get ready to draw the Lewis structure for NH3, the very first thing that we want to do is we've got to determine how many valence electrons does nitrogen have from the periodic table. A normal nitrogen atom on the periodic table, how many valence electrons does it have? And so when I find nitrogen, I notice it's in column 15 or column 5A, which means that it has 5 valence electrons. I also notice from my formula that I have 3 hydrogens, and so I need to determine how many valence electrons does hydrogen have. And I know that hydrogen's in column 1A, which means that one hydrogen has 1 valence electron, So 3 hydrogens has to have 3 valence electrons. Now, once we have our valence electrons, we make a pool. We add these numbers together to see how many total electrons we have to distribute in our Lewis structure. And when I add those together, I notice I get 8. Now, the next thing that you have to do for your Lewis structure is you've got to decide which element is going in the center. And now for this compound, it's not really much of a decision because hydrogen can never go in the center of your Lewis structure. Hydrogen can never go in the center of your Lewis structure. And the reason is because hydrogen can have no more than 2 electrons. So hydrogen does not need 8 in your Lewis structure. The maximum it can hold is 2 because it's on energy level 1. And the maximum number of electrons I can have in energy level 1 is 2. All right, so for this compound, we notice that nitrogen goes in the center of our compound. But to that nitrogen, I have to have 3 hydrogens that are connected. How did I know I had to have 3 hydrogens? Well, because it told me from the formula. All right, now you will notice that when I connected these hydrogens to that nitrogen, I used lines. Those lines, again, are showing that I'm sharing electrons. And so for every line, that means I'm sharing 2 electrons. So from my pool of 8 electrons, I've already used 6 by the 3 lines that I drew. All right. So the next step is I've got to put my pencil down and count and see how many more electrons do each of the elements in the picture need in order to be stable. And so when I count for my hydrogen, again, hydrogen only needs 2, and it's got that line, which means it has 2. That hydrogen needs 2, 1 line, it's got 2. That hydrogen needs 2, 1 line, it's got 2. But when I consider my nitrogen, notice my nitrogen is sharing 2, 4, 6 electrons, but it needs 8 in order to be stable or to have a complete octet. And so I'll notice that I have 2 dots that are left, and I need 2 more electrons to get that to 8. And so because I have 2 dots, I go ahead and place them. And we have now drawn our very first Lewis structure. Now, all of our problems will not be this simple. We'll get to some that are a little more challenging. For example, if I gave you the structure that I asked you to draw for CS2, again, the very first thing that we need to do is we need to figure out how many valence electrons we have. The element carbon we know is in column 14 or column 4A, so it's got 4 valence electrons. The element sulfur we know is in column 16 or column 6A. We know that 1 sulfur has 6 valence electrons, but I have 2 sulfurs, which gives me a grand total of 12 valence electrons. And so I add those together to determine my pool. And I've got a pool of 16 electrons that I need to distribute. So what do I do to distribute these electrons? Well, again, first thing we got to determine is what goes in the center. And again, the rule usually is whatever is furthest to the left on the periodic table or whatever is furthest down, that is what's going to go in the center of your molecule in your Lewis structure. Now we see that the C comes first, so that's the more electropositive elements, so we're going to place that in the center. All right, and to that C, I have to attach 2 H's. Now, I drew 2 lines, so I've got to subtract 4 electrons. And then I'm going to put my pencil down, and I'm going to count how many more electrons do I need to be stable. So when I come to this sulfur, right now in this picture, that sulfur only has 2 electrons because of that one line. So that sulfur has 2 electrons. It needs 6 more in order to be stable. This sulfur likewise needs 6 more. So 6 plus 6 is 12. And then when I count my carbon has 2 lines, which means it has 4 electrons. So it needs another 4. Well, 12 plus 4 gives me 16. But when you look at your pool, you may need 16 electrons, but we only have 12 that we can place. So what do you do when you need more electrons than you actually have? The answer is that's when you use a multiple bond in your Lewis structure. So in my Lewis structure, I'm going to draw a multiple bond. And when I draw that additional line, I've got to subtract out my 2 electrons. And then I'm going to count again. Now on that sulfur, I only need 4 electrons. On that carbon, I only need 2 electrons. 4 plus 2 is 6. But on that sulfur, that last sulfur, I still need 6 electrons. 6 plus 6 is 12. But I don't have 12. I only have 10. All right? And so I need more electrons than I have. I've got to insert another multiple bond. But the question is, where does the multiple bond belong? Now, I could make a triple bond, or I could make a double bond. Which one do you think we should do? And I'm going to tell you what that answer is. What we find is that nature prefers symmetry. Nature prefers symmetry. So instead of adding a triple bond, I'm going to add a double bond to balance that structure out. And when I do that, I have a grand total of 8 valence electrons. So when I count again, how many electrons do I need? I need 4 here. I need 4 there. How many do I need there? None. 4 plus 4 gives me a grand total of 8. And so I would place my 8 dots to have a correctly drawn Lewis structure. Now again, please remember, in your Lewis structure, your lines represent your bonding electrons. Those are the electrons that are being shared between your 2 atoms. Your dots represent your lone electrons. And so those are the ones that are not being shared. So we've done an example where we had only single bonds. We've done an example where we have multiple bonds. But the good thing about Lewis structures is that they actually can be used not only in compounds, they can also be used to draw the structures for ions. So let's say we consider an ion. Let's draw the structure for the ion carbonate, which is CO3 with a 2 negative charge. All right, so we're going to follow the same procedure as we did before. I'm going to want you to pause the video and see what you can do, but without my assistance. And then in just a few minutes, once you finish drawing out what you think the structure looks like, unpause the video and compare what I have to what you have. Now, please notice here that for my pool, when I added up my valence electrons, I ended up with a grand total of 22 electrons. But notice that this ion has a charge, and that charge on this is a 2 negative charge. All right, what does that mean? That 2 negative means that I've gained 2 electrons, and because I gained 2 electrons, I have to add those 2 electrons to the pool. I have to add those 2 electrons to the pool. All right, so determining what goes in the center, we know that we've got carbon. We know that to the carbon is attached 3 oxygens. We use 6 electrons. When we count, I know I need 6 here, 6 here, 6 here, but I also need 2 there. 6 plus 6 plus 6 is 18, plus 2 is 20. I need 20, but I only have 18. So what do I do to solve that problem? Does it matter which one of those O's I make the double bonds between? And the answer is no, it doesn't really matter. We're going to talk about why in just a little bit. And so now when I count, I need 4 here. I don't need any there. I need 6 there, which makes 10. Plus, I need 6 there, which makes 16, which I do have. And so I'm going to place my 16 dots. Now, this problem is very much like the one that we did with compounds. In how you draw the structures, there's only one difference when you're drawing the structure for an ion on paper. And that difference is because I added electrons, because this had a charge, when you draw your structure, once you've completed it, you have to put it in brackets and you have to put the oxidation number outside the brackets. Now, on your homework, you can't do the brackets. So please make sure you tune into the Collaborate video so that you will understand of how you need to properly draw those Lewis structures on your homework assignment. Now, earlier I asked you the question of, did it matter where I put that double bond? And in my drawing, I said, no, it didn't really matter. But if you think about what we talked about earlier, please remember with our single bonds are much weaker bonds that are very long compared to double bonds. Double bonds in this case are going to be stronger bonds that are short. And so if I were to put that double bond, let's say on that oxygen or on that oxygen, would it make a difference? And the answer is, when you're looking at the Lewis structure, yeah, it's a different Lewis structure, but because I can vary which oxygen I place that double bond on altogether, I have created a situation in Lewis structures that is known as resonance. And what resonance means is that there is more than one correctly drawn Lewis structure. So that's one of my Lewis structures. This is one of my Lewis structures. And this is one of my Lewis structures. So that's one resonance hybrid. That's another resonance hybrid. I can also draw a third resonance hybrid where I am including that double bond on the oxygen that is located on the right side of the carbon. And again, all three of these would be different Lewis structures. They would be different Lewis structures spatially, but they ultimately mean the same thing. All right. And so again, when you have this situation is known as resonance. Now, you do have questions on your homework about resonance where you will have to draw multiple resonance structures. Please make sure that you read the directions for how to draw those Lewis structures, because if you don't follow the directions, it will count your Lewis structures incorrectly. And so that takes care of our Lewis structures. Now, please remember though, all of your Lewis structures are not going to be as straightforward as the ones we've done, because there are also exceptions to your octet rule. And those exceptions, there are 3 of them. You could end up with your Lewis structures where you have when you get your pool, you end up with an odd number of electrons in your pool. And if you end up with an odd number of electrons, there's no way you can make pairs for all of your atoms. And so one of your atoms is going to have an odd number of electrons. And so that's an exception to the octet rule, where all your elements won't have 8 valence electrons. Another exception is, what about elements where it's impossible for you to give everything 8 valence electrons, like in BH3? Well, in BH3, again, you don't even have 8 total valence electrons in your pool. So you can't give things 8 if you don't have 8 electrons in the pool to start with. All right, so that's another exception to the octet rule. And then the last exception to the octet rule is, sometimes you'll have structures where elements are required to have more than 8 valence electrons. So when would a central atom have to have more than 8 valence electrons? And one example of that would be if I were to give you the structure PCl5. Please notice in that structure, there's one P, but you have 5 Cls. Well, if you draw that structure, you'll notice that those 5 Cls have to attach to that one P. All right, and so that means that the P is going to have more than 8 valence electrons. Now, when can you have a hypervalent central atom? And it is true that you can have a hypervalent central atom if that central atom is an element that is in row 3, a non-metal in row 3, row 4, row 5, row 6, or row 7. So any of those elements that are in row 3 or higher, they can be hypervalent. Why can they be hypervalent? Well, because remember, they've got d orbitals or a d sublevel that does not have any electrons in it, because I've not gone to that next row to complete that number of subshells that I need to have. And so because those d subshells are there and they have nothing in them, I can place electrons in them in order to get them to have what they need. Now, again, on your homework with your ions, you cannot place the brackets. So what do you do because you cannot place the brackets? Or anytime you have a resonance structure and there's more than one correct Lewis structure, what do? And the answer is, you've got to determine the formal charge for your elements. And you've got to choose the Lewis structure that gives you the lowest formal charge for each of your elements. Now, let's say we do an example of formal charge. The very first thing you need to know is, what's the formula to calculate the formal charge? What's the formula to calculate the formal charge? And the answer is that the formal charge equals the number of valence electrons for that atom, minus the number of lines minus the number of dots. The valence electrons minus the number of lines minus the number of dots. So in order to calculate a formal charge, you actually have to have a Lewis structure drawn. And so let's say we draw the Lewis structure for, let's pick something we haven't done yet. Let's do Cn negative. So when I calculate my valence electrons, carbon has 4, nitrogen has 5. When I create my pool, I've got 9, but you'll notice that there's a negative sign, so I have to add. Now, what if on your ion your charge is positive? What do? Well, positive means that you've lost electrons, so instead of adding to your pool, if it was a positive charge, you would have to subtract from your pool. All right, so with Cn negative, I have a pool of 8 valence electrons. So when I draw my structure, I've got C and I've got N. They have to be connected to one another. When I count, I need 6 there. I need 6 there. That makes 12. I only have 6. What do? Draw another line. Count again. I need 4 here. I need 4 there. That makes 8, but I only have 4. So what do? Draw another line. How many do I need here? I need 2 here. I need 2 there. But I only have 2. So what do? So when you draw your structure, let's see, I subtracted out 2 for the first line, 2 for the second line, 2 for the third line. What we're going to do is, because the nitrogen, because the nitrogen is more electronegative, we're going to put those 2 dots on the nitrogen. Oh, no, that's not a problem. I can't add. 9 plus 1 is 10. So when I subtract, that gives me 8. Then when I drew my other line, so now I have 4. All right. And again, you can see mistakes happen to the best of us. So I place 2 dots there. I'm placing 2 dots there. This is going to go in brackets, and there's going to be a negative charge on the outside. So when I get ready to calculate my formal charge, if I'm considering my carbon element, when I look at carbon on the periodic table, it has 4 valence electrons. In this picture, how many lines does it have? It's got 1, 2, 3. So I'm subtracting out 3. How many dots do I see? I see 2. So when I get my difference, that difference I end up with is a -1. So this C will have a negative charge on it. When I calculate the formal charge for my nitrogen, nitrogen on the periodic table has 5 valence electrons. Notice I have 3 lines. I have 2 dots, which gives me a value of 0. So on your homework, what you've got to do is you're going to show all of this with the formal charge on your elements. Now remember, formal charges of 0, that means you don't have to show anything. But if it does have a negative formal charge or a positive formal charge, you have to show it on your molecule that you're drawing on the screen, okay? And you also would not have the brackets. So on your homework, the way you're going to represent your Lewis structure is like this, where you have that negative sign being on the carbon because that's the formal charge for that particular element. Now, you can practice with formal charge on any of the Lewis structures that we've already drawn, but please don't forget that formula. You will definitely need that formula in order to calculate formal charge. Now, again, the formal charge, or the one that is chosen, is going to be the one that gives us the lowest possible formal charges on our structures. So when you have more than one possible Lewis structure, calculate the formal charge, and that'll show you which structure is the correct structure. All right, then in chapter or section 7.5, you start talking about bond energies. And remember, when we talk about bond energy, we're talking about how much energy does it take to break that bond apart. And is that process endothermic or exothermic? Do you have to absorb energy or do you release energy? Your book then proceeds into talking about the lattice energy, or the energy for your 3-dimensional ionic compound structures. How much energy does it take to break that lattice apart? And that value is a measure of how strong the bonds are between them. And so that again will tell you how rigid that 3-dimensional crystal lattice is. Now, your book then moves into Vesper theory, which deals with the three-dimensional orientation that your molecules take. And let me tell you that in order to have a correct Vesper three-dimensional structure, you have to first draw the Lewis structure. You have to first draw the Lewis structure. Um, with that Lewis structure, you can see around your central atom how many pairs of bonding electrons you have and how many lone pairs you have. Your book gives you an excellent chart that talks about your electron pair geometry as well as your molecular geometry on page 370. Please remember, when we consider Vesper, you've got to look at your central atom to determine what the three-dimensional structure shape is going to be looking like. Make sure that you are familiar with the information that you see in that chart on page 370, because with any of your Lewis structures, you should be able to tell after you've drawn the structure what your three-dimensional orientation is going to look like. So please make sure you read over that molecular geometry information. And that is pretty much it for chapter 7. Um, if you've got any questions on anything, please reach out. If you don't understand the directions on your homework, please let me know. Please make sure that you attend the Collaborate session for the week. Or if you are unable to be there for the session, please make sure that you watch the video. I will be going over how to input your homework answers. If there's anything I can do to help you, please reach out. I hope this video has been helpful. If you need any other assistance, I have placed lots of resources on the course page to help you with this week's homework and the information in Chapter 7. I look forward to seeing you again soon. Have a great rest of your day.